Hello. Today we're going to be talking about reduced row echelon form and row echelon form of a matrix. And we're going to be using it to solve this system of equations. So here we have two equations and four unknowns. So the first thing I'm going to do is get rid of the variables in a way which we can compartmentalize them in terms of a matrix. So I'm going to go ahead and create my matrix. My matrix will consist of these coefficients. So I have 4, 12, -7, -20, and 22. In my second row, I have 3, 9, -5, -28, and 30. So really, this holds the system of equations, but it holds it without using the variables. If you wanted to think of the variables as well, the variables would be in the columns. So you would have the first column being x, the second being y, the third being z, and the last being w. This row over here is sometimes called the augmented row, so sometimes you'll see some sort of line separating those two. And these will just be your constants over here. So we're going to perform this elementary row operation to turn the system into first row echelon form and then reduced row echelon form. The first thing we need to do is create a pivot. Usually how I create a pivot is I look in the first row and column and I try to make that 4 a 1. The way I usually do this is just scaling the row. That's one of our elementary row operations. So I might document my steps by saying, I'm going to take 1/4 of row 1 and then just store it in row 1. So that's what I intend to do. If I scale every part of row 1 by 4, I would have the 1 which I desire. 12 by 4 is 3. I have a fraction here, which makes life a little bit more difficult. -20 by 4 is -5. And 22 by 4 is 11/2. The second row will be just how it is there. I've created what I call a pivot. And a pivot is a leading one in a row and column. So that first one is a pivot now. That's great. So once I create a pivot, I want the number under it, or any other numbers under it, to be 0. Usually how I accomplish this is I multiply a row, the pivot row in fact, by the opposite of that number and add it to the next row. So the way I'll accomplish getting that 0 is I'm going to take -3 times row 1 and add it to row 2, and we'll store it there. The first row will be exactly how we have it here. So I'll still have 1, 3, -7/4, -5, 11/2. Now, I want to multiply the first row by -3 and add it to the second row. -3 times 1 plus 3 is 0 by design. It turns out when you take -3 times 3 and add it to 9, you also get a 0. That might have been sort of unexpected. -3 times 7/4 is 21/4. 21/4 plus -5, that's -20/4, is 1/4. -5 times -3 is 15. 15 plus 28 is -13. And finally, 11/2 times -3, -33/2 plus 30, which is 60/2, gives us 27/2. Okay. At this point, some books would call this row echelon form. Our book has another criteria, and this should have been stored in row 2, so let me just add that in on the fly here. I think I said that, but I didn't write it. So notice what I have here. I have this pivot here, zeros underneath, and here is another pivot. So technically that's a pivot. Technically most books would call this row echelon form. Our book doesn't, because notice that for each row that does not consist entirely of zeros, the first non-zero entry is a 1, called a leading one. So to create row echelon form for this matrix, we're going to have to turn this into a 1. That's not so bad to do, though. So remember, to create ones, pivots, I just have to scale this second row. So what I will do is I will take 4 times row 2 and then just store it in row 2, and that will create my pivot. My matrix will then be first row the same, second row scaled by 4, 0 times 4, 0 times 4. This should be a 1, and it is. 4 times negative 13 is negative 52, and 4 times 27 halves is a 54. At this point, even according to our book, we have what we call REF, row echelon form. Notice with the definition above, all rows consisting entirely of zeros occur at the bottom. There are no rows of zeros here. For each row that does not entirely consist of zeros, the first non-zero entry is a 1, called a leading one. We have that. Here's a leading 1, and here's a leading 1. And finally, for 2 successive non-zero rows, the leading 1 in the higher row is farther to the left than the leading 1 in the lower row. So that's true. It's sort of a stair-stepping configuration there. And that's REF. Now this could be used to solve the system. However, if we use RREF, that's going to give us our solution a little bit easier. So as a remark, a matrix in row echelon form is in reduced row echelon form, or RREF, if every column that has a leading 1 has zeros in every position above and below its leading 1. So really, the last thing we would have to do to turn this into our REF is create a 0 here. And we can do that by multiplying that second row by 7/4 and adding it to the first row. So let's do that. 7/4 row 2 plus row 1, store in row 1. Now we have to be careful because we're using fractions here, but we should be able to do this. So our first row, of course, when we multiply a 0 by 7/4, we'll still get 0. So the first row is not going to change until the third entry. That third entry should be a 0. 7/4 times 1 minus 7/4 is 0. Now we have to be careful. 7/4 times negative 52 is negative 13 times 7, which is negative 91, plus negative 5 is negative 96. Finally, 54 times 7/4 is going to be 27 halves times 7, which is 189 halves plus 11 halves is 200 halves. 200 halves is, of course, 100. And we copy down our last row. And what we have accomplished is reduced row echelon form. So this last step is satisfied now. If every column that has a leading one has zeros in every position above and below its leading one, we are in reduced row echelon form. And sometimes I'll refer to that as RREF. Let's go ahead and solve the system now. So to solve the system, we put our variables back in. Before we solve the system, we should make some notes. Let's note that we have two pivots here. So X is a pivot and Z is a pivot. We'll say that our X and Z variables are pivots. But Y and W don't have leading ones. We call Y and W variables free. So I say they're sort of free to do whatever they want to do. So they're free to be whatever they would like to be. If we turn this back into a system, this is what we're looking at. We will have 1x plus 3y plus 0z minus 96w. And the augmentation is our constant is 100. We will have 0x plus 0y plus 1z minus 52w is equal to 54. When we look at pivots and free variables, each pivot we should be able to solve that variable in terms of the other free variables. All the other variables are free. Sometimes when I do have a free variable, like y and w, what I will do is say y is free, so y can be whatever it wants to be. I'll say y is equal to y. It's only with free variables. And w can be whatever it wants to be. So w is equal to w for all real numbers. So this would really be my system here. I should be able to solve for my pivots in terms of the free variables. So if I subtract 3y over and add 96w over, I solve for x. My y is a free variable. I'm reordering the variables. My z is a pivot. I solve for z in terms of the free variables. Z is equal to 54 plus 52w. And finally, w is free, which means w is equal to w, where y and w are any real number. This is the solution to my system. What that means is that if I let x, y, z, and w satisfy these equations, they will satisfy this equation. Really what that means is I'll have an ordered four tuple where I can choose anything I want for the free variables. If I choose 0 for w and y, one of my solutions would be 100 for x, 0 for y, 54 for z, and 0 for w. So that would satisfy my solution. Another solution might be if I chose 1 for y and 0 for w, I would have 100 minus 3. I would have 1 for y I would have 54 because W is 0 and W is 0. This would be another solution. I don't have to choose integers. I can choose any real number. It goes on and on and on. I hope this has helped with the difference between reduced row echelon form and row echelon form. Also, how to solve a system by hand. Thank you.